Most organic compounds we encounter contain only covalent bonds, and the most common bonds are those between consecutive carbon atoms, allowing carbon to form long chain compounds, such as octane, and ring structures, such as cyclohexane. When we look at these structures, we see the consecutive carbons bonded together with covalent carbon-carbon bonds. However, we know that these compounds also contain a number of hydrogen atoms. So, where are they? The convention in organic chemistry is to draw what we call the skeletal structure of the molecule, and this is what we're showing here. We show all of the bonds that are present except the carbon-hydrogen bonds. The reason for this is simple. It makes the structure much clearer and the diagram far less cluttered. By remembering a simple rule, however, that normally carbon always takes part in 4 bonds, no more, no less, we can logically deduce the number of hydrogen atoms which must be present, even though they're not shown. Take for example the compound citronellol on your screen. We can look at each of the carbon atoms and by remembering that they must all have 4 bonds, work out how many missing hydrogens there must be on each carbon. The numbers are shown in red for each carbon atom. So why is it that carbon forms 4 bonds? And how does this influence the nature of organic compounds? When we think of the structure of an atom, we normally think of the Rutherford model, with the nucleus consisting of protons and neutrons, and the electrons whizzing around in planetary-like orbits. There's just one slight setback with this picture. It's completely wrong. Quantum theory tells us that electrons are not really little balls of negative charge located in one place, but are actually more diffuse and spread out, more like clouds of negative charge. And just as clouds in the sky can change shape and drift and be pulled around, so can these electron clouds. In organic chemistry, we find that there are 2 main shapes to these electron clouds, or orbitals, which concern us. Firstly, there are s orbitals, where the electron cloud looks like a sphere around the nucleus of the atom. Then there are p orbitals, where the electron cloud adopts a figure of 8 shape around the nucleus. As we'll see later, it's these p orbitals which are involved in forming carbon-carbon double bonds. Here, the p orbital is orientated along the x-axis, but we could easily orientate the orbital along the y or the z-axis. This is why p orbitals tend to come in sets of 3. Each of the 3 orbitals orientated along a different axis, and we call them px, py, and pz. Now, what has all of this got to do with organic chemistry? If you were able to look into an atom of carbon, you would find that it has 4 electrons in its outermost shell of electrons, and these are arranged in s and p orbitals. For reasons we don't need to go into here, we find the arrangement would look something like the left of this diagram, with 1 electron in an s orbital and 3 electrons in p orbitals. But carbon has a real trick up its sleeve. To get greater stability, it takes these 4 electron clouds and merges them together, just like clouds in the sky might merge into a different shape. When it does this, it forms 4 new hybrid orbitals called sp3 orbitals, and these are shown on the right of the diagram. The key with these orbitals is that all 4 have the same shape, meaning that when the carbon atom forms bonds using these hybrid orbitals, it will form 4 bonds only, and all of these bonds will have the same shape and length. It is this that gives carbon compounds like methane their regular shape, with each carbon atom sitting at the centre of a tetrahedral geometry. You can see the four sp3 hybrid orbitals overlapping with the spherical s orbitals from the hydrogen atoms, forming the covalent bonds in the methane molecule. And we term this type of bond a sigma bond. It is the regular bond you find in nearly all organic compounds, when a carbon atom is bonded to four other atoms via single covalent bonds. But what about compounds where carbon forms double bonds to other carbon atoms, as we'll see later in these videos? What is the difference in this type of bond? Well, to form a double bond, carbon firstly shares one of its p electrons with another carbon atom. These non-hybridized electrons effectively form a bond above and below the carbon atoms called a pi bond. This now leaves each of the carbon atoms with two p electrons and one s electron, and carbon again combines these to form hybrid orbitals. But in this case, the hybrid orbitals are called sp2 orbitals, and most importantly, there are only three of them. So now, when each carbon atom uses these three hybrid orbitals to form bonds, we get a different shape around the carbon. The best way to arrange three bonds is not in a tetrahedron as before, but in a triangle shape within the plane. So we describe the shape around each carbon atom as being trigonal planar. If you look at the three green sp2 hybrid orbitals around each carbon atom, you should be able to see this shape. Now we can actually go further and possibly use two of the p electrons to form two extra bonds between the carbon atoms, resulting in a triple bond between the carbon atoms. We see this bonding in the alkynes. So what would the shape look like around each of the carbon atoms this time? Now each carbon has used two p electrons, forming the extra two bonds between the carbon atoms. This means that each carbon only has one p and one s electron left to form hybrid orbitals, and so both carbons form two sp hybrid orbitals. Now the best way to arrange two orbitals is in a straight line, meaning that the shape around the triple bond is linear, a straight line. So to summarize, carbon normally forms four bonds. And by doing this, it can form chains and rings. Electrons are found in clouds called orbitals, and the two main types of orbitals are s and p. Carbon combines its orbitals to form four sp3 hybrid orbitals, and these are arranged in a tetrahedral arrangement. But in the alkenes, three sp2 hybrids are formed, giving the alkenes a trigonal planar arrangement.